Hi everyone, this is T. Ramesh, Assistant Professor, Department of Mathematics of Dr. SNS College of Arts and Science. The last lecture series video, we discussed what is queuing system and what are the basic characteristics of queuing system and a different formula. From that, we calculate what is length of the system, length of the queue, waiting line in the system, waiting line in the queue. So everything we form using the formula. Now apply the formula. We calculate uh, this all kinds by a problem. Okay, let us go to the video. This video topic is analyzing an MM1 model, that is single server MM finite capacity. Okay, right. So analyzing an M1 model. So first we discuss the first problem. This presentation explains how to calculate expected queue length in a simple M1 queuing system. So learn step-by-step calculations using arrival and service rates. First, understanding the M1 model. Single server, that is one server handle all customers sequentially. Poisson arrival we calculated because the infinite number of customers arrive the system. Therefore, customers arrive randomly at an average rate of lambda. Suppose it takes some 8 hours. Exponential distributions, the service time is exponentially distributed with the rate of mu. Okay, lambda means 8 hour. So mu, so mean service time. So how calculate mean service time is also given 3 minutes per customer. Okay, so convert this to service rate mu. How calculate service rate mu? There are minute in 3 minutes per customer. So 1 hour we have 60 minutes. So 60 by 3 is equal to 20 customers get per hour the service. Okay, so arrival is 8 customer and the service is 20. Right. So what is arrival rate? Arrival rate is lambda, that is equal to 80, and the service rate is 20 customer per hour. So we calculate these two. These two are very important to find length of the queue, length of the system, and so on. Okay. So lambda is 8 and mu is 20. Okay. So now we formula for expected queue length. So in MM1 Q formula, what is the LQ, length of the queue? That is lambda square divided by mu into mu minus lambda. Already we have lambda is arrival rate or customer per hour and mu is service rate customer per hour. So first step, we calculate lambda square. So what is lambda? 8 hours. What is lambda? 8 customers. Therefore, 8 square is 64. Next, we calculate the denominator term in the formula. So, denominator term is mu into mu minus lambda. Already we have mu is 20. So, 20 into 20 minus 8, that is equal to 20 into 12, that is 240. Step 5, we put it everything in the formula. That is lambda square divided by mu into mu minus lambda. So, lambda square is 64 and the denominator value is 240. So 64 by 240 after reducer we get a 0.264 uh, is a is the length of the cube. Okay. Interpretation of the result. So what this result? So 0.267 customers waiting on the queue. So what is that? Low queue length indicates high service efficiency. Implementations. What is implications here? Most arrival experience little to no waiting. That's all. Okay, summary and what's the next step? So identify the model, confirm the system MMM assumptions, calculate the rates, that is we calculate lambda and mu and apply the formula, that is length of the queue is lambda square divided by mu into mu minus lambda to find the expected queue length and validate, interpret it, the result, improve the system design. So these are all the concepts of the first problem. And we discuss the second one. So second one MM model. Second, this represents a focus on MM1Q model characteristics by Poisson arrival. So this scenario involves the service center with a mean arrival rate is 3 units per hour and the mean service rate is 10 minutes. So these two are given, that is directly lambda is 3 units and service mu is 10 minutes. So our objective is to determine these three crucial performance metrics: the utilization factor rho, the probability that exactly 2 units and 2 units are present in the system, and the expected number of waiting units waiting in the queue. So understand this matrix is essential for effective resource allocations and ensuring smooth service operations in context modeled by queuing theory. Okay, we go one by one. So what is the lambda? Lambda is already given. We calculate first what is the utilization factor or the um, the row utilization factor row, that is rho is lambda by mu. Already the lambda value is 3 units per hour, and the mean service rate mu is 10 minutes, 10 minutes. So we converted to hour, that is 10 by 60, that is 1 by 6 hours. So service rate mu is in 6 units per hour. So already we take 1 by 6 minutes per hour. So convert to hour, it is 6 units per hour. Therefore, lambda value is 3 and mu rate is 6. So what is utilization factor? Rho is lambda by mu, that is 3 by 6 is 1 by 2, that is equal to 0.5. So what's the meaning? This means the service center is busy 50% of time, indicating moderate utilization and a capacity to handle incoming minutes. Okay, now we calculate what is the formula, nth of the probability for n customers in the system. That is, probability for n is 1 minus rho into rho power n unit in the system. So already we have the rho value is zero point 0.5. Already we done it. So there are two customer in this. What is the probability for two customer in the system? That is n is equal to 2. So 1 minus rho is zero point 0.5 into rho power n. Zero point 0.5, the n is two customers, so 2. So 1 minus zero point 0.5 into zero point 0.5 the whole square. So zero point 0.5 the whole square is 0.25, and 1 minus zero point 0.5 is zero point 0.5. So zero point 0.5 into 0.25 is 0.125. So what does it indicate? What is interpretation of this? That is the probability that exactly 2 units occupies a system both in service and in queue is 12.5 percentage. Right. So what is expected number of units in the queue, LQ, that is rho divided by 1 minus rho, length of the system and the length of the queue calculated. So rho divided by 1 minus rho, that is rho is zero point 0.5, 1 minus rho is 1.5, 1 minus zero point 0.5, that is equal to zero point 0.5 divided by zero point 0.5 is 1 units. So what is rho? Already we have it is zero point 0.5 units on averages. So length of the queue is L minus LS, that is 1 minus. Already we have the length of the system, that is a zero point 0.5. So 1 minus zero point 0.5 is zero point 0.5. So what is the meaning? This means on average there are zero point 0.5 units waiting in the queue. Units waiting in the queue indicates minimum con consciousness under current conditions. So these everything is calculated the length of the system and the length of the queue using the formula. Thank you.